We will learn to evaluate, and we will also start to learn to graph polynomials. So the first thing we want to do is just do some definitions here. So we have a polynomial is a monomial or a sum of monomials. So poly means many, so we've seen monomials, binomials, which is two terms, and trinomials, and then we have polynomials. A polynomial function is a function that has the form that you see on your paper. So f of x equals a sub n, x to the n, and then it goes down to our constant term. So this very last a sub 0 is considered a constant term. And it says where a sub n does not equal 0, so that very first term cannot equal 0. The exponents are all whole numbers, so that one's very important. So exponents have to be whole numbers, which do not include your negative numbers. And the coefficients are real numbers, so meaning we won't have imaginary. The leading coefficient in the above term, the one that we're just staring at, would be your a sub n. It's the coefficient that leads the others when your polynomial's in standard form. The degree in our example is just n. It's that variable right there. And the constant term in our example is your a sub 0. The polynomial is in standard form if the terms are written in descending order. Let's go ahead and spell descending correctly. Order from the exponents from left to right. So we always want to make sure that you start at the highest exponent and work your way down. So you went x to the third, then x to the second, x to the first, and then your constant term. So the next part, we're going to go ahead and fill in this chart. Oops, sorry about that. We're going to fill in some different common polynomials. I'm going to go ahead and zoom in here. So a degree 0 is what we call a constant term, or a constant polynomial. A degree 1 is linear. Degree 2 is what we spent all of last unit working on, are your quadratics. Degree 3 is a cubic function. And fourth degree polynomial is called a quartic polynomial. For the standard form, I went ahead and just filled in that column because that would have been a lot for me to say as I was writing it down. So go ahead and pause the video while you have a chance to jot this standard form down into your notes. And in this last column are all examples of what each of those types are. So we have your, on the top we have your constant, which is just a constant number. Your linear equation, which is in slope-intercept form in this case. We have our quadratic, and in this case it's in standard form. And then cubic and quartic. So this first example first asks whether or not the polynomial is, or the equation is a polynomial. So if I take a look at h of x, the first one, it's x to the negative second plus x minus 4. And right now I can tell you that this is not a polynomial because this leading term right here has an exponent that's negative 2. And we cannot have a polynomial that has exponents other than whole numbers. So this one is not a polynomial, which means that the rest of the chart does not apply because you can't have a standard form, it won't have a degree, and so forth. So for number 2, we have t of x, 5x squared minus 3x to the 4th plus 10x minus 6. So if I take a look at all my exponents, they are all whole numbers. So this one is a polynomial. And in standard form, we have to write it in descending order of our exponents. So we'll have t of x equals, and if I look at my terms here, I notice that I have an x to the fourth term. So I have to rewrite this so this is first. Now keep in mind that this is a negative 3, x to the fourth. So that'll be written as our first term. And then after that will be the 5x squared plus 10x minus 6. And the degree of this polynomial is simply, when it's in standard form, simply the highest exponent. So the degree here is a 4. And then the type, that's depending on what we just wrote up above. So that if it's a degree 4, that means it's going to be a quartic equation. And the leading coefficient is just the coefficient of the first term. So here's our first term, and the coefficient there is negative 3. So the leading coefficient is negative 3. Just always be careful that it's in standard form before you pick out the leading coefficient. So number 3, we have f of x, and then we have the square root of 3x squared plus 1/2 x minus 5. All of my terms here have exponents that are whole numbers. It's x squared, that's a whole number, x to the first, and then 5. Now a lot of times people get thrown off because you see the square root of 3. The square root of 3 is just a coefficient, not an exponent. So this would represent a polynomial, and it is already written standard form because the highest exponent is 2, and that was already first. So I'm just going to rewrite that equation. The degree is the highest exponent. So if I look at this first term, the highest exponent is 2. And a polynomial that has degree 2 is called a quadratic. And the leading coefficient is the coefficient of that same term that we looked at for the degree. So the coefficient here is the square root of 3. And number 4, so here we have 2 to the x power minus 1. Well, 2 to the x, remember our exponents need to be whole numbers. We don't know what x represents, so this one cannot be a polynomial. The next concept we're going to work on is what we call synthetic substitution. Synthetic substitution is a way that we can evaluate a polynomial at a certain x value without having to do direct substitution, which is where you simply just substitute the value of x into the polynomial. So over here on the left, I have it already set up for you. So the x value that we're evaluating this polynomial at goes out here on the outside of what looks to be a sideways L. So we're going to evaluate this at 2. And then along the top here is a negative 3. That matches up with the negative 3 that's in our polynomial. And then 1 is the coefficient of x squared. Negative 12 is the coefficient of x, and negative 5 is the constant term. So the way that synthetic substitution works is that you bring down the very first term that you see. So we see a negative 3, so I'm going to bring that straight down below the L. And then you're going to multiply the x value on the outside, which is 2, times negative 3. And that number will go underneath the next number that's in our along the top. So 2 times negative 3 was negative 6, and I put that under the 1. And now you're going to add the two numbers that we see. So you're going to add 1 plus negative 6. And that number is going to go below the line. So when I add 1 and negative 6, I'm going to have negative 5. And I'm going to do that same process again. I'm going to take 2 times negative 5, which is negative 10. And I'm going to put that underneath the next number, which is negative 12. And then I'm going to add negative 12 and negative 10. And that'll give me negative 22. And then again, I'm going to multiply the 2 again, but this time by negative 22. 2 times negative 22 is negative 44. So that will go under the negative 5. And then I'm going to add negative 5 and negative 44 to get negative 49. So what that represents is if we were to find f of 2, we evaluate the function when x is 2. The final answer will be just this last number that we wrote down, so negative 49. Now on the next problem, it does have a note, and it's a pretty important note, so you might want to highlight it or circle it somehow. Be sure to include a coefficient of 0 for any missing terms, and that also includes the constant. So we do need to include placeholders here. So in number 7, we have an x to the 4th minus 2x cubed, so we went in x to the 4th and we dropped down to x cubed. And the very next term is just x to the 1st. Well, in the middle there we're missing an x squared term, so we'll need to put a 0 as a placeholder when we do our synthetic division. As well as at the very end we're missing a constant term after the 4x, so we're going to have to add a 0 there as well. And we're going to evaluate this polynomial when x is negative 3. So that value will be on the outside, and along the top are our coefficients. 1, because it was 1x to the 4th, then negative 2, and then again we're going to add that 0 in there for that placeholder for the x squared, 4, and then again that placeholder for the constant. So the process is you drop the first number down straight below, and then you're going to multiply negative 3 times 1, and that'll go underneath the negative 2. And then we'll add negative 2 and 3. Then we'll multiply negative 3 and negative 5, and add 0 and 15. And then we'll multiply again, negative 3 and 15 is negative 45. We'll add 4 and negative 45 to get negative 41. And then the last step, negative 3 times negative 41 is going to be a positive 123. And then we'll add 0 and 123 to get 123. So the way that we write our answer is f of negative 3, so it's the value of the function when x is negative 3 equals 123. And here we're just going to be starting the basics for graphing polynomials and talking end behavior. We did something a little bit earlier, maybe yesterday or the day before, talking about a little exploration on end behavior. This is just some notation that we're looking at, and it's not something you need to necessarily memorize this entire chart. You just have to understand the idea of it. So if you have an odd degree function, so if you have a degree 1, 3, 5, so the highest exponent is 1, 3, 5, 7, and so forth, then you will have an odd degree polynomial. Odd degree polynomials have end behaviors that go in different directions, different directions. So the arrows will go, one will go up and one will go down. That's really kind of what you need to know for odd behavior, end behaviors. And over here we also have an odd behavior, and the arrows go in different directions. So now it really just depends on the leading coefficient. So the right arrow, the right end behavior, will tell you what your leading coefficient is. So if the leading coefficient is positive, as in the first one here, the right arrow will go up to positive infinity. And if the leading coefficient is negative, then the right arrow will go down. And then for even degree functions, we're talking about the arrows that go in the same direction, just like a quadratic. So if it's, again, the leading coefficient determines the right end behavior. So the right arrow determines whether or not your end behavior or your leading coefficient is positive or negative. So in this case, it's positive because the right arrow is going up. And over on the bottom right, the bottom arrow here, the bottom right arrow is going down, so our leading coefficient is negative. And you notice that the arrows are going in the same direction. Now this is what we call limit notation when we talk about end behavior, and it's read the limit of f of x, or the limit of the function, or y value, remember f of x just means y, so the limit of the y values as the x's approach negative infinity. This is called the left end behavior because as x goes to negative infinity, that's going to the left. That means that it's on the left side. Your x's are going to negative infinity. What it's asking is what's happening to your y values. Well, if I look down here, my y values are going to get smaller and smaller and smaller because that's going to travel down because there's a down arrow. So our y values are going to go to negative infinity. And then on the right side, it's the limit of f of x as x approaches positive infinity. So as x gets bigger and bigger, what's happening to our y values? So if I look on my graph, x is getting bigger and bigger. The y values are going to get bigger and bigger to positive infinity. The next limit notation is, again, read the same way, the limit of the f of x, or limit of the y values, what's happening to the y values as x goes to or x approaches negative infinity. So as x gets smaller, meaning to going to negative infinity, what's happening to your y values on the left side? Well, this arrow is facing up, so as x gets smaller, your y values are going to get bigger to positive infinity. And on the right side, as your x values get bigger, that's to the right, your y values are going down to negative infinity. The other two will work the exact same way, but for even-powered polynomials, the end behaviors will be the same because they go in the same direction. Odd go in different directions, so if one's negative infinity, the other one's positive infinity. So let's take a look at the next part. In the last couple questions, it says, in the following graphs, state whether the degree is even or odd, or the leading coefficient is positive or negative. So in number 10, I look at first at my degree, and I know that my left arrow is going up, so my left end behavior is to positive infinity, and my right end behavior on the right side, the right arrow, is going down to negative infinity. They're in different directions, so the degree is going to be odd. And to look for the leading coefficient, you look at the right arrow. The right end behavior is pointing down because it's going to negative infinity. So the leading coefficient in this equation would be negative. For number 11, again, I'm looking at the left end behavior. So that would be negative infinity. And my right end behavior will be positive infinity. They are in different directions, so that also will be odd. For the leading coefficient, you look at only the right end behavior and determine whether it's going up or down, and the right end behavior is going up. So that means that you're going to have a positive leading coefficient. And the last problem, the left end behavior is pointing down, and the right side is going down. So that means that this is going to be an even degree polynomial because the end behaviors are the same. And the leading coefficient is determined by this right side. This right arrow is pointing down, so that would be a negative leading coefficient.